Okay, so I'm gonna try a little different arrangement. Um, so I don't have to get up and down on my knees all the time. So today in this video, I want to talk about the Hall effect. It's a really important effect. It's the only non-quantum based experiment effect or experiment that I'm aware of that can be performed, which will distinguish whether in an electrical current, it's actually the positive or negative charges which move. So when we talk about a wire, we will say that we have a current moving along the wire. How do we know that it's, say, a positive charge moving this way, or does that positive current that we define correspond to a negative charge going the other way? How do we know? That's the point of the Hall experiment. Okay, so it's a famous experiment, and you guys should all know what it does or what it did. Many of you took took linear electrical circuits with Tim, and you should have, I think he has you guys write a paper on the Hall effect. So hopefully some of you guys already know what the Hall effect is. If not, that's okay. I'll explain it. All right. So the trickiest thing is understanding the picture of what's going on. Just a warning, in sapling, there is a question on the Hall effect or something very similar to Hall effect, I can't remember. But if I remember right, the diagram is terrible. So just kind of be careful with the orientations of things. All right. So that's why it's important. So what you have to understand for the Hall effect, or what you have to imagine, is that you have a wire that is kind of thin, like a ribbon, or I usually describe it as a stick of gum. So it's a wire which is going to carry a current, and it kind of has the geometry of a stick of gum. Okay, so there's a current, I, and the current's going to flow this way. And let's go ahead and set some geometric parameters. The width of it, we're going to call that W. And we'll call this depth, we'll call that T for thickness. Okay, the thickness is going to be T. And notice the cross-sectional area would equal T times W. All right, so T times W is the area of a cross-sectional slice through there. Now, so we're going to have a current flowing along the body of the stick of gum, or the ribbon, and then we're going to have a magnetic field, and I want to do that in red. A magnetic field which is going to go perpendicular to the stick of gum. Okay, so we're going to have a magnetic field which threads through the body of the gum like that. This is my magnetic field. All right. So that's the basic underlying idea of this. So hopefully that's clear. Just I want to remind you guys of some things that we've kind of seen. We're going to pull together a bunch of little facts about circuits and new things that we've learned about magnetic fields. So notice or remember, we said that the current I could be thought of as a current density J, and it's really the J integrated over this face, but we're going to assume it's a uniform current if you wait long enough and let things settle down. So it'd be J times A, where J is equal to the charge per carrier. I'm just going to call that Q. That's the charge of each little element that's actually moving. I'm going to call that Q, times the number of charge carriers per volume. That's going to be a number per volume. So this is going to be a charge per volume when I multiply it. And then I'm going to multiply that times the average or typical drift velocity of one of the charge carriers. Okay, so if you're working that out, that has units of charge times, so charge per carrier, carrier per volume. So that's going to be charge per volume times meters per second. So that's going to be charge per second times a meter. Sorry, that's going to be charge per second times a meter divided by a volume. So that ends up being charge per second divided by area, so that when I multiply by area, I get charge per second or current. Okay, so remember that. Now, in a typical metal or something which is a good conductor, the number of charge carriers per volume is roughly the number of atoms per volume, because roughly each atom contributes one electron. If it's an insulator or some other material, then you'd have to come up with some other way to estimate that. I'll comment. I'm not sure. I kind of made a guess as to what you might imagine doing. Well, I'll talk about that towards the end. Okay, so that's some stuff that we learned about currents. The other thing we learned last couple videos, is that there's a magnetic force. The magnetic force on a charge carrier, on a point charge, is the charge of the object times the velocity of the object cross the magnetic field coming from the sources. We haven't yet talked about how to make magnetic fields. We will eventually. And then you could combine the magnetic force with the electric force to find the Lorentz force, which is the total electromagnetic force on a point charge. And that's Q, positive or negative, times E plus V cross B. Okay, so that is the full formula for the electromagnetic force on a point particle. All right, so the Hall effect is, and the result that is obtained from that basically is to take this formula and this fact about currents and apply it to this situation and see what pops out of it. All right, I'm going to redraw our stick of gum from a bird's eye point of view. It makes it easier to see things. So I'm going to have my stick of gum. Well, from the bird's eye point of view, I just see a rectangle. Okay, the width is W. The thickness would be into the board, so I'm not going to draw that. It's there, though. And I have a magnetic field into your eye. Okay, so the magnetic field's going into your eye, out of the board. All right, the current was flowing, it's going to flow up. The current's going to flow up. So that's fine. Now, we have two possibilities. And they are either that the thing that moves has a positive charge, in which case it would be moving with the flow of what we call positive current, or given what we call positive current, if the things that actually move are negative charges, they'd be flowing the other way. So what we're going to do is first just make a guess that they're positive, draw a picture of what happens, and then we're going to draw a picture of what would happen if, hypothetically, they were negative charges that move, and we'll get a different result, similar but different. It's going to be a minus sign issue. and then experiment will be the thing that actually resolves the difference to figure out what actually happened. So let's start by assuming Q is greater than 0, and I'm going to just write that as Q plus, and then I'll have Q minus when it's the other way. Okay, so in the positive case, let's imagine then we want to have a current going this way. Now let's focus on the very first bit of charge that sits there. So you get a little bit of charge that comes in. Let's assume initially it's flowing straight up. So we're going to have Q plus, and it has a drift velocity going straight up. And then let's think about and we're going to assume that the rest of the charges are more or less neutralized, that they are in place. Okay, so I'm going to imagine that I've got these background charges kind of in the atoms that are there that are kind of neutralized, and so they're more or less irrelevant. I'm just looking at the charges which are mobile. Okay, so I'm going to write down the magnetic force on this. Okay, the magnetic force is going to be Q times V cross B. And this is a positive charge, so I'll put a little plus there just so I remember what I'm doing. Okay, the formula, so Q is positive, the velocity is up, and the magnetic field is into your eye. So I have to work out the cross product. So I have to align the palm, or the heel, the heel, I guess, of your left hand. Align it with the velocity and curl your fingers from the velocity towards the magnetic field. Up, there. So the V cross B points to the right, and Q is positive, so the force is to the right. So what's going to happen is that this particle is going to feel a force to the right. It's actually going to, do it in blue. It's going to wander over here, and you're going to get a positive charge right here. Okay, but we don't move just, electrical current isn't just one charge, it's a bazillion of them. So you let this go and go and go and go and go. And what's going to happen is, so this charge went over here, and it actually turns out, because of charge neutrality, you're effectively going to get a negative charge on this side, and then you keep running it, and they keep just kind of flowing over. Okay, and you get a bunch of plus charges, and then they would induce negative charges on the other side. Okay, so you'd end up with a big pile of pluses over here and a big pile of minuses. And eventually, okay, so that's what would happen. Now, it's a little more complicated, though, for each successive charge, because once you get a pile up of charges here, and you try to follow the next charge in, well, the next charge starts to see the electric field that the previous charges have built up. And the electric field is going to exert a force, so the field lines are going to run to the left, and the electric force is going to go to the left on a positive charge. So what's going to happen is you're going to get magnetic forces to the right, electric forces to the left, and the Lorentz force, which is the total force, is going to be the sum of the two effects. So the total force, the force Lorentz, is going to be Q plus times the electric field plus V cross B. And what you should imagine is you run this forever and ever and ever in a day. And eventually you get a huge pile of charge here, a huge pile of charge here. And then you follow what happens to the last, a bit of charge once you reach steady state. Well, once you reach steady state, what's actually going to happen is you get a balance between the positive charges on one side pushing, electrically, versus the magnetic force pushing it to the right. So you're going to get equal electric and magnetic forces on this last bit of charge that you would add. And because they balance, that means that this term in parentheses would equal 0. So if you wait long enough, the kind of induced electric field, or the accumulated, maybe is a better word, accumulated electric field is going to cancel the magnetic force on this particle. And that's the case that we want to study. Okay. So we're assuming that the charge is positive. So if the electric field is equal to, well, so minus the electric field equals V cross B, so that they can cancel out. And if I want to look at the magnitude of this thing, well, remember we had that the electric field is the derivative of the potential with respect to in this case, it'd be the x direction, and there'd be a minus sign there. Really, though, I'm not worried about the minus sign because I'm just going to, we know that the positive charges are here. And so the voltage you would have, the voltage is across we're going to talk about a voltage across the stick of gum, not along the length of it, but across the width of it. And we know that it's high near the positive charges and low near the negative charges. So I know that if I go from left to right, you're increasing the voltage in this situation. So if I just worry about magnitudes, I would find that, oh, and the other thing is, it's important, because from the point of view of an electron, this stick of gum might as well be a parallel plate capacitor, right? It might as well be a capacitor. So I can go ahead and just say, this is like the difference in potential divided by the difference in position, which is just the width. So when I pull this all together, take the magnitude of everything, I would get that delta V divided by the width equals, well, I could write that as V drift, right? The velocity of each particle would be the drift velocity on average times the magnetic field. They're because the velocity and magnetic field are perpendicular, there's no sign of theta to worry about. Okay, and oh, you can rearrange this if you want. All right, now, so here's the point, the big picture, before we get into details. Big picture is this. Because of the magnetic field, you get a curving of charged particles. If you assume that the things which are moving are positive, they're going to go, say, on the right with the magnetic field given. And you're going to be left with a bunch of negative charges that accumulate are induced, if you want, on the left-hand side. And eventually, if you let the charges accumulate, you get a balance between the forces. And what happens is there is what's called a Hall voltage. The Hall voltage is the voltage not along the stick of gum, but across the width of it. And basically, what you would do is, okay, so what would happen is, and with positive charges and a magnetic field into your eye, you're going to get positive charges accumulating this way, which means that the potential would be higher to the right. I'm going to keep this formula here, but what I'm going to do is just redraw the situation. If now we assume that instead of positive charges moving, let's assume that the thing that actually moves is negative. Now, the macroscopic numbers are the same, right? We're not changing, right? It's the same stick of gum and a current, and we're just trying to say, what if this current, which flows upwards in the presence of this magnetic field, which is into your eye, what if it actually had negative charge carriers? So let's just see what happens if that was the case. If the charge was actually negative, so I'll put a minus there to remind us. Well, if this upward positive current was built out of moving negative charges, well, that would actually mean that my negative charges were moving down to produce this positive current flow. And okay, that's fine. So let's work out what the magnetic force would do to this guy. So I'd say, all right, so the force magnetic would be Q minus, which is a negative number, times V cross B. Okay, now let's think about what's happened. V, the velocity, is now down. The magnetic field is external. It's still into your eye. So I have to do V cross B. Oh, so V cross B is now pointing to the left. Not surprising. The velocity is reversed, so this cross product is reversed. But the force isn't just V cross B. The force is Q times V cross B. And so there's a minus sign in the velocity. There's another minus sign in the charge. And so V cross B is to the left, but the force is back to the right. And so what happens is, in this situation, hypothetically, if the things moving around were negative, you would actually accumulate negative charges over here. And consequently, you would expect there to be an induced positive pile of charges on the other side. Okay, this would be the picture you had if the charge carriers were negative. Before we worked it out hypothetically, what it would look like if the charge carriers were positive. Now we're doing the same for what if they're negative. It's the same basic picture. It looks roughly like a capacitor. So the magnitude formula for the potential is going to be the same. All we're talking about is a minus sign. In this situation, for the same magnetic field and the same current, you actually have negative charges on the right and positive charges on the left, which means if you look at the transverse or the voltage across the stick of gum, you actually get the negative charge, the lower potential on the right and the higher potential on the left. So what you find is basically you take your voltmeter, you make the stick of gum, you run the current through in the presence of magnetic field, you measure the voltage across the two sides, and you say, oh, was the right side higher or lower than the left? If the right side was higher than the left, then the charge carriers must be positive. If the right side was lower potential than the left, then the charge carriers must be negative. We do the experiment, it turns out they're negative. Electrons have negative charge. Okay, so it turns out charge is less than 0 by experiment. You can't argue on theoretical grounds, it's just you have to do an experiment to say. And as far as I know, that's the only classical experiment you can do which knows the difference. I suppose there might be some spin-off where it wasn't just the stick of gum shape, but the point is this balancing of electric and magnetic forces. That's really the key effect. This is called the Hall effect, this splitting of the direction of the charges, and it creates a Hall voltage, which in absolute values has this term, or this form. I'm going to massage this into something a little bit more useful or interpretable. But make sure point number one is to understand that the way the Hall effect works is by causing these particles to move, and by measuring whether it's higher potential on the right or the left, you can determine whether the thing moving is actually an electron or positive or negative charge. All right, so that's the first thing. The other thing I had, remember, I had that the current equaled Q V drift, QV times the number per unit volume times the area, which means that I could write the drift velocity as the current divided by the charge on each charge carrier times the number density divided by the area of the kind of cross-sectional slice, which would be into the board as I drew it. All right. Okay, going back to the formula I had for the Hall voltage, I had that delta V Hall equaled, I've erased it, so I have to do it from memory here. So that's going to be the drift velocity times the magnetic field times the width of the stick of gum. But I can substitute in for the drift velocity, the current, and I get delta V equals I times B times W divided by Q in over A, the area. But the width over the area is nothing other than 1 over the thickness of this. So this quantity is 1 over the thickness, T, the depth into the board. So if I rearrange this, I can solve for Q times N, and that equals I times B divided by the Hall voltage and the thickness. Okay. Whew. Why is that a big deal? Well, so not only can the Hall effect tell you whether the things that move are positive or negative, look at what happens. The left-hand side is microscopic. This is like the charge on an electron, only maybe you don't know about electrons. So this is the charge on whatever the thing is moving. This is something about the atomic structure of the material. It's microscopic information. On the right-hand side, you have a current, which you can measure. You have a magnetic field, which you can control with a magnet or something. The Hall voltage, you can measure. And the thickness is something you engineer. It's how much you cut the piece, the size of the sample. So what you can do then is by making a sample, controlling the magnetic field, and then measuring the current and the voltage, you can estimate the charge of each charge carrier, namely the electric charge for an electron, and then the number density of the charge carriers. Now, I claimed that it was roughly 1 carrier per atom is contributed. I don't know. I would think, though, so to measure this, you would need some sort of experiment which did not depend upon electrical phenomena. Just off the top of my head, what I was imagining was you could probably look at thermal conductivity, because when you have a metal, we know they conduct heat very well. The reason they do that is it's actually the electrons which carry the heat. So it's the same carriers which carry electrical charge are also carrying the energy in thermal conductivity. So if you look at thermal conductivity, you should be able to estimate the number of carriers involved. And so basically you could get in from another experiment. And once you knew that, you could use that to measure the electrical charge. There's a famous example of this with the fractional quantum Hall effect, which was an effect discovered in '83, I believe. And they were looking at some material, some exotic material. And they were looking at this kind of experiment to measure, what was actually moving around inside the material. So they're looking at it, and then it was noticed that it was noticed that the thing which moved around, same kind of idea, didn't move with charge equal to E or 2E or 3E or some integer number of E, which would be easy to understand, right? Because if it moved the charge E or 2E or 3E, it could be some sort of maybe it was an electron, or maybe it was an ionized atom that was actually doing the thing that moved, or something like that. Or maybe it was doubly ionized, could be like an alpha particle or something like that. But something standard, integer units of E. In fact, in this fractional quantum Hall effect, this isn't what happened at all. What came out was something which had a charge of like a third of E. What would that mean? Does that mean that the electron has been split into thirds? It turns out it's more complicated. So it turns out in that case that it's not a system where you can describe it in terms of simply little moving point particles. Turns out you have these sort of, you can think of them as like whirlpools or vortices that carry charge, and because of topological kind of, if you want, fancy quantum mechanical conditions, the things that actually move, effectively, these whirlpools have some charge in the middle, and then swirling around it is sort of a fluid, quantum fluid, I guess, for lack of a better word, and that kind of shields the charge, but it doesn't just shield any fraction, it has to be a rational number's worth. And so, anyway, it's an interesting story. These kinds of effects, these topological objects, have a whole host of interesting features. Some of those kinds of features might be useful for quantum computing someday. So anyways, the fractional quantum Hall used the basic Hall idea to measure the charge of the charge carriers, and it's famous because it was weird. It didn't come out to be something easily explainable. It had to do more with complicated whirlpools of quantum matter, and it's famous for that reason. So Nobel Prizes were given for that. Anyway, okay, so that is the quantum Hall effect. I only said a couple words about the fractional quantum Hall effect. That's not at this level. That's a more involved discussion. So, all right. See you guys next time.